So thank you very much for the introduction. So yes, exactly. So today I'm going to give you a non-exhaustive and perhaps a bit biased overview of the developing field of quantum simulation. Right. So as you will see, it is not accidental that this talk sits in between Dr. Brewer's talk on relativistic heavy ion collisions and Dr. Plaket's talk on quantum error correction. In fact, quantum simulation is something in between a physics experiment and a quantum computation. So to walk you towards the philosophy and the practice of quantum simulation. So let me start from the very basic. So science is about making quantitative observations of phenomena, then formulating a theory or a mathematical model to explain these observations, and making new predictions out of the model. So an important part of our job as theoretical physicists is to be able to compute the physical behavior that results from a model. Okay? So usually the simplest predictions can be obtained by explicitly solving a model, right? However, in the general case, explicit solutions are not available, and we have to resort to a cascade of less and less pretentious strategies to solve the problem. For example, we may want to do a brute force simulation of the model, usually using a computer, or we may want to resort to controlled approximation schemes, or if none of these work, we can try to replace the model with some simpler phenomenological model, right? So let me take a minute to remind you how this works in the context of classical mechanics, right? So one of the early drives to develop classical mechanics was to explain planetary motion, right? So the motion of a single planet orbiting around the sun is described by Newton's equation. This equation can be explicitly solved, and this exact solution tells us a great deal about the astronomical observations, right? Now, when we move to the problem of many celestial bodies, so call n their number, we deal with n Newton equations, right? We deal with n Newton equations, and this problem is famously non-solvable even for n equals 3, right? What we can do instead is performing a brute force computation of the trajectories of the bodies. So how do we do that? Basically, we use Newton equation. So the state of the system is described by 6 times n variables, so all the positions and all the velocities of all the bodies, right? And we use Newton equation to update these 6n variables for the next time step, so for a short time step. And we repeat this process over and over to compute the full trajectory. Now, using modern computers, this can be done very efficiently for thousands or even millions of bodies, right? So it's fair to say, that this problem is, so that the brute force numerical simulations are extremely powerful in this problem. And here in this animation, I hope you see it. Yes, you see a computer animation of the trajectories computed for a many-body gravitational problem, computed using a computer. Okay, so this is the situation. Now let's move to quantum mechanics, right? So quantum mechanics, the original drive to develop quantum mechanics stemmed from a problem of atomic spectra, for example, hydrogen, right? So we deal with the motion of a single electron orbiting around the nucleus, right? And this is described by Schrödinger equation. Now, Schrödinger equation, in this case, is explicitly solvable, and the exact solution of this problem tells us a great deal about the observation of atomic spectra. So great, so far so good. Now, and here you see the illustration of some of the atomic orbitals that stem from the solution. Now, problem comes when we move to the problem of many quantum particles, like, for example, problem of n electrons, right? So in this case, we deal with the Schrödinger equation, with the m-body Schrödinger equation. And this problem, of course, is famously non-solvable, even for n equals 3, just like in the classical case. But here there is something much worse happening. Essentially, the n-body Schrödinger equation describes the evolution in time of the m-body wave function of the system, of the wave function of n electrons, right? So this wave function is nothing but a complex number assigned for every possible classical configuration for the n particles, right? So imagine these particles, let's be generous and say that these particles can be in a given number of states, say 10, or even 5, or even 2, right? Just every particle can be in 2 states. Now, the number of configurations of the system is 2 by 2 by 2 by 2 to n times, right? So it's 2 to power n. So essentially, we have the system is described by 2 to power n numbers, complex numbers, right? And we have to, this is the many-body wave function, right? Now, this wave function, as you see, the complexity of this object explodes exponentially with the number of particles. And I'm sure, I think that in the recent pandemics, pretty much everyone got a sense of how quick an exponential growth is, right? So this is, we could try to estimate how bad this is for a real problem of interest. Actually, so we could try to convince ourselves, but then here instead I reported the words from a Nobel lecturer, Walter Kohn, 1999, who argued, even provocatively argued, that the many-body wave function, the quantum many-body wave function, is not a legitimate scientific concept. So the essential point here is that the amount of information that you would need to describe the wave function of many electrons, for example, quickly exceeds the amount of matter in the entire universe. So even for 1,000 electrons, this would exceed the amount of matter in the entire universe. So this is the bottom line here is that, so you may agree or not with this strong viewpoint, but the problem is real. So the problem of the exponential wall is real, right? So it's not really about technological advance. It's not about building a better and stronger supercomputer. So there is a fundamental limitation in the capability of computers to deal with quantum many-body physics, right? And this is something new. It's different from classical mechanics. So I think it's fair to say that brute force numerical computations of quantum many-body problem are fundamentally out of reach. Okay, and this is actually why if you try to Google quantum many-body physics or quantum many-body wave function, as you could do, for example, for the previous, in contrast with what you did with the previous images, here you find just a bunch of funny and incomprehensible drawings that we theoretical physicists like. And this is because essentially it's very hard to even visualize this massive, huge amount of information encoded in the many-body wave function. Okay, so basically quantum many-body theory calls for countless approximation schemes and phenomenological theories, and this includes, for example, what you have seen in the previous talk by Dr. Brewer. Okay, so this is it. But then you may legitimately wonder at this point, why do we even care about solving the quantum many-body problem, right? So after all, for example, a football is made of many quantum particles, as far as we know, but we can predict its behavior extremely well, right? So why do we even care about solving the quantum many-body problem? So the point here is that many important phenomena in nature are intrinsically quantum and intrinsically many-body, in the sense that ignoring quantum effects or ignoring correlation effects between the particles is not a good idea to describe them, right? And here I will give you a non-exhaustive list of some problems that would be very nice to solve if we could deal with the quantum many-body problem, right? So in the domain of chemistry, for example, if we had a solution of the quantum many-body problem, this would allow us to perform a first principle computation of molecular structure, for example, or reaction rates of chemical reactions, or this would allow us to predict, give us the opportunity to predict new molecules, for example, with obvious applications, for example, for drug design and so on. So here in the illustration, you see an example. This is basically a so-called light harvesting complex that plays a role in the process of photosynthesis, and it's an example of a process where quantum mechanical effects are important. Now, let's move to the domain of condensed matter physics. This is close to what I actually do, right? So here, solution of the many-body problem would give us first principle computation of the properties of materials, for example, of their structure, of their out of equilibrium response, and so on and so forth. And this would give us the opportunity to predict new materials or new phases of matter, for example, the conditions for having high temperature superconductors, and this would obviously be extremely important for applications, right? And finally, also in the context of high energy physics, so solving the many-body problem would give us first principle computation, for example, of hadronic structure, nuclear matter, right, or nuclear reaction rates, and this would give us the opportunity to predict the behavior of matter in extreme conditions of temperature and pressure, for example, in the early universe dynamics, or in the inner of stars, or in relativistic heavy ion collisions, as you heard in the previous talk by Dr. Brewer. So this would obviously be extremely interesting also in this context. And these are all examples coming from natural sciences, but actually there are examples that go beyond the domain of physics. I think Dr. Plake will briefly touch upon this aspect in the next talk. Okay, so the summary of the situation is the following. So basically, solving the quantum many-body problem would lead to a huge progress, to a huge leap forward in several branches of science, right? So this would be really great. However, we have said that brute force numerical computations are fundamentally impossible. On the other hand, controlled approximations, in many cases, are known to suffer badly, right? Otherwise, we would have solved all these problems. And phenomenology is not always satisfactory, of course. So this seems like a bad situation. So his natural question is there a way out from this simulation? And as you can guess from the fact that I'm giving this talk, the answer is, a possible answer is yes, in the sense that there is a possibility that was suggested in the early 80s by Richard Feynman that is actually the content of this talk, which is the possibility of performing quantum simulations. So basically, the fundamental idea is the following. So if we can't store and process a many-body wave function on a classical computer, which is made of units that can be in two states, either 0 or 1. So the point is, because this would say for the problem of 1,000 electrons, this would require a computer as big as the universe. But then why don't we store and process the information contained in this wave function, for example, in 1,000 electrons? Why don't we store it and process it using a processor that is made of quantum units, that is made of quantum particles, like, for example, 1,000 atoms, right? So provided we can operate with these objects, manipulate them quantum mechanically, right? Not classically, but quantum mechanically, then we only need 1,000 particles to simulate 1,000 particles. We don't need something as bigger than the universe, right? So this is the central idea that was central insight that was proposed, right? And this goes under the name of quantum simulation, right? So the goal is to simulate quantum many-body problems using a controllable quantum many-body system, right? So this is this looks like a strange idea. Just invite you to pay attention to the rest of the talk, where I try to make it a bit clearer. So how do we simulate a quantum system using a quantum machine, using a set of quantum devices? So the most important thing is that we need a new type of hardware, right? So basically what we need is a highly controllable quantum many-body system where we can access, control, manipulate, observe individual quantum particles, which operate in a way that is not somehow affected or not disturbed or not destroyed by for example, by environmental processes, right? Okay, so we need this kind of machine or hardware, right? And suppose we are given such a machine. So suppose we are given a quantum many-body system that we can control, maybe not perfectly, but we have a good degree of control on. So what do we do with it? How do we perform a quantum simulation of our system of interest? For example, our favorite molecule, our favorite material, our favorite nucleus, or whatever you like. So what do we have to do? So first thing first, you have to essentially encode the states of the system of interest in the states of your hardware. So you need a mapping, a correspondence between the states of the system of interest and the states of your quantum particles. So this mapping can be more or less obvious, more or less direct, right? In some cases, it's very direct. In some cases, it's very convoluted, very abstract, and you need some imagination to build this correspondence. But it doesn't matter. You just need one correspondence between the two, right? Second, we need to be able to prepare this system in the state that we need, in the state that we like, for example, and this is where the control enters, right? So we need to prepare it in a wave function that represents the wave function that we care about. Then, and this is usually the bottleneck, we need to be able to design the forces, or technically the Hamiltonian, that governs the system in a way that mimics or resembles the forces or the actual evolution of the system of interest, right? And here is where most of the pain comes, right? Because your system has its own native interactions and doesn't want to do what you want, right? So you have to be somehow drive it into doing what you want, right? And finally, you have to be able to measure the observables of interest. So there is some observable that you care about in the actual system, and you have to be able to map it back to your hardware and be able to measure this precise quantity. Right? Okay, so basically, all this set of requirements can be summarized in a single equation, which is the one that you find in the bottom of the slides, which expresses the equivalence between the quantum many-body dynamics happening on one side, on the actual system, and on the other side, so in your artificial hardware, right? So basically, this correspondence is about constructing a dictionary between your system of interest and your hardware. If you are able to do this, then you can perform your quantum simulation. And of course, this is not easy in general, and that is already in the paper by Feynman. You see a remark on how difficult this can be. But of course, this is one possible way to proceed, right? Okay, so before going on to tell you about examples, right? So to tell you about where we stand in this enterprise and what can we do now, what we can hope to do next, right? I want to give you another little piece of theory and draw an important distinction between two approaches to quantum simulation. So one that is called analog quantum simulation and one that is called digital quantum simulation. So analog quantum simulation is close to what I described so far, right? And is actually, in the examples that I will give, I will talk about analog quantum simulation. So analog means essentially that your hardware, your quantum system, has some native interactions, right? And basically, the cards that you can play two cards essentially, right? So you can use additional engineering in the system to tweak these native interactions to take the form that you want, right? Or you can somehow devise clever mappings, some clever counterintuitive mappings that map your native system to some system that superficially looks very different, right? But this is what you would like. So you can play these two games essentially, and so basically you have your system. It functions more or less in the way it wants to function up to some massaging, right? This is an analog quantum simulation. Now, digital quantum simulation is a priori something very different. So here, the principle is different. So the idea is that you want to switch on and off. You want to be able to switch on and off your units, your individual units of your quantum hardware, such that you can address them individually and perform individual operations on them. So on each one of them, or maybe pairs of them, right? You want to be able to perform these building block operations that we call unitary gates, right? And then the idea is that an arbitrary quantum dynamics for the full system of n particles can be approximated arbitrarily well, provided you are given a large enough set of gates, of unitary gates. So the idea is that you have to form a set of gates that you can efficiently implement, right, in such a way that these gates form a universal gate set, right? Universal gate set means that an arbitrary quantum dynamics can be approximated by a sequence of these building blocks, right? So you can decompose it in a sequence of unitary gates, right? That is also called a quantum circuit. So basically, in an analog quantum simulation, you don't need to devise some strange or clever mappings. All you need to have is a software, right? So you need a program that compiles your target evolution that you want in your actual system. It compiles it in terms of a sequence of gates, right? Or a circuit. So in this illustration, you see what a quantum circuit looks like. This is an illustration. So in this case, time flows from left to right, right? So on the left, we have our initial quantum units that are prepared in some reference state. Let's call it 0. Okay, so this is our initial state, right? Then we have our digitized evolution, so our sequence of unitary gates, right? And this is created by a software that creates it in such a way that this sequence of gates reproduces exactly the dynamics that we want, right? So these funny boxes and drawings are drawn from some set of gates, some special set of gates, right? And then at the end, on the right, we measure the qubits. And the answer to our problem is encoded in this measurement. So you see that the power of the digital machine is that it's hardware independent somehow. It can approximate arbitrarily well any quantum dynamics in principle. So it's universal. So in this sense, this is kind of the ultimate goal of the field and this is why the analogy between these things and a classical computer is the reason why we call this a quantum computer, right? So you will hear more about this in the talk by Dr. Plake, but here I can't help mentioning the fact that in the development of this field of universal quantum computation, the researchers in Oxford played really a protagonist role, so including David Deutsch and Arthur Eckert and Andrew Steen and so on and so forth. So this is a very important topic worldwide and here in particular. Very good. So right. So this is what we would like to do, right? So if you never heard before or thought about or thought before too deeply about quantum simulation or quantum computation, I hope I conveyed the message that this is a very exciting theoretical idea, right? But then where do we stand in the implementation in the implementation of this idea, right? So there are several competing experimental platforms that are participating in the race to build somehow a more and more powerful quantum machine, right? So there are very, very many by now. Here I reported 2 pictures that illustrate two kind of families of these quantum devices. On the left, we see the so-called AMO family, so the atomic, molecular, and optical systems. And on the right, we see so-called solid-state systems. So in the pictures give you a rough idea of what these devices look like, right? But an important point to stress here is that these devices are, at the moment, these devices are kind of imperfect. So they are called NISQ devices, meaning noisy intermediate scale quantum devices. And here the problem is that the size of these devices is limited, and the coherence time, so the time where these machines works in a quantum mechanical way, is also limited, right? So roughly speaking, you may say that the boundary, the frontier of current quantum devices is more or less at the boundary of classical computation. So on the task where we think that these objects would outperform classical computers, at the moment they can compete with classical computers, right? And it's kind of a active topic of research to try to make proof of principle experiment that provably beats what a classical computer can do, right? So this is the current state of the art. Of course, the holy grail of the field, the ultimate goal, is to build a scalable and fault-tolerant quantum computer. So this would give us unlimited size and unlimited coherence time, right? So you will hear more about this in the next talk by Dr. Plake. Now, I just want to say that this, of course, many of us believe that this will come, right? And a huge amount of people are working to make this possible. This of course, will need a lot of work and a lot of effort. Good. So, okay. So what I'm going to do in the remaining part of the talk is to essentially give you an overview, a selected overview of some of the experimental platforms that constitute today some of the best analog quantum simulators that we use to somehow to study quantum many-body physics and try to solve quantum many-body problems. And then I will describe, at the end, I will describe one successful example of a quantum simulation performed using these devices that is drawn from my own work. Okay, so let's go there. So I will focus on family of quantum simulators that is called that go under the name of cold atom quantum simulators. So cold atom quantum simulators are essentially the effort to produce them originated from the effort to produce essentially to the efforts in low temperature physics. So to produce the coolest somehow system that functions in a quantum mechanical way, right? So what they have done essentially is to isolate, so to trap a gas of atoms to confine them in a region of space and to cool them to extremely low temperatures in the order of nanokelvin, right? Using also, various experimental techniques that were developed for this purpose, right? So disclaimer here: I'm a theoretical physicist, so this is not what I do personally, right? But I will try to give you somehow a flavor of how these things are done. So okay, so essentially these gases are trapped and cooled to extremely low temperature using several techniques. And in this cooling process, this is where the number of particles is extremely reduced compared to macroscopic samples, but still it's we obtain a very cold gas, which still contains a lot of atoms, right? And the crucial point here is that the temperature is lowered to such an extent that the de Broglie wavelength, right? So the wavelength associated with the quantum mechanical nature of the motion of these particles is comparable to the size of the confinement region, right? So when this happens, it means that the quantum mechanical nature of these objects cannot be ignored, of the motion of this object cannot be ignored anymore, right? And this is how people realized, for example, the first Bose-Einstein condensate, so the first an exotic phase of matter that was not observed so far was not observed before by cooling this gas of bosonic atoms. Okay, so this is what you do, and then of course when people successfully realized this very cold gases, then they realized that these systems somehow they have all the control techniques that they have developed to do this somehow could be pushed forward and maybe used to realize this Feynman's dream of a fully controllable, isolated quantum many-body system, right? So this is how it originated, right? So people try to develop other experimental techniques to control the interactions between these particles. For example, the strength of the interaction between particles, or the shapes or the range of interactions, or the selective interactions, so certain particles preferentially interact with certain others, and so on and so forth. So all this kind of engineering can be achieved with atomic molecular optical techniques, right? And this is an important step in the realization of a quantum simulator, because remember what I said before, we have to be able to tweak the native interactions of the Hamiltonian to mimic the behavior of our preferred system of interest. Of course, the atoms are just atoms. They don't know that they have to simulate the relativistic heavy ion collision, right? So we have to do something for that. Okay, so we can control interactions, and we also experimentalists develop very advanced imaging techniques. So to somehow measure, remember in this list of requirements, there is also the requirements of being able to measure individual particles, and this is something that today people can actually do. So there are very advanced imaging techniques that basically give us access to spatiotemporally resolved measurements in the system. Okay, so this is the playground. Okay, so one development that stemmed out of this efforts is the so-called optical lattices. You can view optical lattices as a sort of analog quantum simulator for condensed matter physics in the following sense. So condensed matter physics is about electrons moving in a solid. So a solid is a crystal, right? Is a periodic structure, regular structure, and electrons move in this periodic structure, right? So what people managed to to realize in the field in the context of cold atoms is essentially to realize periodic potentials by using lasers, right? So basically, arranging counterpropagating lasers, we can form standing waves, right? And these standing waves generate a potential that is felt by the atoms. So the atoms now move in a periodic potential, pretty similarly to what electrons do in materials, right? But with important differences. So one crucial difference is that this is just a potential. So the crystal is not dynamical itself. So as we say, there are no vibrations of the crystal. There are no phonons. And this makes our system much more coherent, much more isolated, right? And second, there is a difference of scale. So electrons are tightly packed together in materials, and you can hardly imagine to visualize, to pick one single electron and control it and visualize it, right? While here, this is completely programmable, right? So we can decide the lattice spacing of this system, right? So we can basically realize cold neutral atoms that are very heavy, very slow, and very distant from each other, right? And jump from one potential well to the next of this sort of egg box, right? And interact with each other. So basically, and this is fully programmable in the sense that the geometry of this lattice is completely customizable, right? As you see in this representation, where people manage to confine the atoms in arbitrary predefined geometries, right, to form these figures. So the Hamiltonian, the kind of the forces that govern this system, the native Hamiltonian takes this form. So it's not important to really understand what it is. But what I want to stress is that this term, proportional to J, is associated with the tunneling of neutral atoms from one side of the lattice, so from one bottom of the well to the next. And this U term instead corresponds to the interactions when two atoms sit on the same lattice side. So this is kind of a simulator this very closely resembles the kind of Hamiltonians that we have in condensed matter physics. And this is why this created a lot of excitement, because we can now we can very directly simulate Hamiltonians of interest in condensed matter physics. For example, the Hamiltonian that is thought to govern high temperature superconductors. Okay, so now there is, as I said, there is additional engineering tools that we can apply, right? And here the creativity of people was really stunning, right? For example, we can use a speckled pattern for our lasers to create a quasi-random, to superimpose a quasi-random potential on this lattice, right? And this mimics the fact, the motion of particles, of quantum particles in a disordered potentials. So in this way, we can study phenomena like Anderson localization phenomena, right? That was originally proposed for the motion of electrons in the impurity band of a semiconductor. Okay, then another interesting thing is that you can shake, right? You can periodically vary your optical lattice, right? Just by moving it in time, you can shake it in a single direction, or you can shake it circularly. And interestingly enough, essentially this periodic shaking gives rise to artificial, for example, to artificial magnetic fields. Now, these atoms are neutral, so they are not sensitive to magnetic fields in the sense of orbital magnetic field, but you can engineer such artificial magnetic fields by this additional toolbox, essentially. And this was realized in previous years. And finally, another example that I report is that we can use internal spin states. So the atoms have internal states, right? And these internal states can be used to mimic an extra dimension of the system. So what they call a synthetic dimension. So we can basically simulate the motion of a higher dimensional system by using internal levels of the atoms. So you see that you can really play with your creativity and engineer very interesting mappings between your native hardware and your target Hamiltonian of interest, your target system of interest, to study many more or less obvious quantum many-body problems. Okay. And of course, as I said, one of the ultimate goals in this game is to study open problems in condensed matter physics, for example, the elusive mechanism for high temperature superconductivity. Okay, so this is so much for optical lattices. Another very interesting platform that is gaining a lot of traction in recent years is the so-called neutral atom processor. So in particular, what is called Rydberg atom arrays, right? So here, essentially, we have still cold gas of atoms, in particular an alkali atom, so a hydrogen-like atom, right? And here, the particular thing here is that atoms are trapped in what is called optical tweezers. So essentially very tightly focused lasers that form microtraps for the atom. So basically, we can trap individual atoms in individual traps. And the advantage here is that then we can move around these traps and fully reconfigure the geometry of the system. So this is one. So the geometry is one piece of the analog simulation. The other super important piece of this analog simulation is essentially the ability to fully program the strength of interactions between these particles. And this is done by exciting the atoms to so-called Rydberg states, so to highly excited Rydberg states, right? So essentially, we program our lasers, right, to drive transition between the ground state of these atoms and a very highly excited state, right, where essentially the electron that orbits around the atom occupies a very high orbit, so a very distant orbit from the nucleus, right? So the wave function of this electron is very big, right? The advantage of this is that the atom now has a giant polarizability, so it has giant interactions. Let me show you how it happens. So before that, the Hamiltonian that describes the dynamic of the system basically has these pieces. So this is a piece that drives the transitions. Basically, the atoms are described as two-level systems, the ground state and the Rydberg state, right? And this piece describes the transitions between the states. Then we have the energy difference between the two states, and then we have these interactions, which I'm going to describe. So these interactions are basically dipole-dipole interactions or van der Waals interactions that are controlled by the distance, right? And the special properties of this system is the following. Essentially, if we picture the ground state of the wave function of the electron in the ground state of this atom, it looks like this small blue dot, right? This is the electron orbiting near the nucleus. Now, when the atom is excited to the Rydberg state, so to a highly excited state, its wave function looks more or less like that, right? So basically, this electrons forms a giant wave function and has a giant polarizability. Now, when we try to simultaneously excite two nearby atoms to the Rydberg state, the dipole-dipole interaction between them is enormous. So this is energetically prevented somehow. So we have the phenomenon of Rydberg blockade when these two giant wave functions overlap. Essentially, it becomes impossible to simultaneously excite these two atoms. And this mechanism can be very efficiently exploited to create entanglement between atoms, right? And this is described by this piece in the Hamiltonian. So here, to show you the high degree of control with the geometry, essentially, this is a movie that was created by the Michel Lukin's lab in Harvard. Essentially, these are nothing but Rydberg atoms trapped in these microtraps, in these optical tweezers, and reconfigured in arbitrary shapes to create essentially arbitrary geometries and arbitrary animation, as you see in these old video games. Okay, so this is another platform. And finally, last but not least, another platform that I wanted to mention is trapped ions, right? This, of course, plays a special role here in Oxford. Here downstairs at Beecroft Building, we have one of the world-leading labs to realize ion-trap quantum computing, right? So led by David Lucas and Chris Balance, and also the Oxford also played a role in the sort of inspiration of this technology, right? So dating back to Arthur Eckert, Andrew Steen, and so on. So this is really something important here in Oxford, right? So trapped ions has a similar principle, except that these are ions, not atoms, in the sense that these are ionized atoms, so they are charged, right? And they basically, okay, let me skip the details here, but they are still trapped in using some special traps for charged particles. And the point is that we end up with some, especially in this geometry given by the Paul trap, we end up with a crystal, one-dimensional crystal of atoms, of ions, sorry, that are trapped electromagnetically, right? And the atoms, the internal, so we can use the internal levels of these atoms to store quantum information, right? So these atoms can be in two states, right? And these atoms are able to interact, so to talk to each other via the vibrations of this crystal. So this is like, imagine a system that is floating in the vacuum, trapped with these electromagnetic fields, right? Then there are some vibrations of this crystal, right? And this vibration coupled to the transition between the internal level of the system. And basically, if you go through the math, you end up with a Hamiltonian of this form, where you have some type of Ising model, right, with this spin-spin interactions. And again, this can be viewed as an analog simulator for condensed matter models, right? So some sort of quantum magnet in the most obvious sense, in the most native sense. Very good. So this is some of the leading experimental platforms that realize analog quantum simulation and also, hopefully at some point, digital quantum simulations. So in the remaining time, actually, I have less time than I thought, but in the remaining time, I want to tell you just one example of how you can use these simulators, these quantum simulators, to realize somehow in a slightly non-obvious, well, not slightly, in a non-obvious way, to realize quantum simulations of problems of interest in other fields, right, in other contexts. So in particular, I want to present one example coming from, in a way, going in the direction of high-energy physics, right? So I want to talk about simulating quantum field theories, right? So like the theories of fundamental interactions using these quantum machines, right? Now, this is a very, very, very difficult problem. Unlike condensed matter physics, where I showed you that there is some more or less direct analogy between the kind of Hamiltonians you can realize in quantum simulators and the kind of Hamiltonians you would like to realize, right? Because they mimic the problem of interest. In high-energy physics, this is much more difficult. And the problem is the following. So there are many problems. So one is that theories of fundamental interactions have usually at least two kinds of particles. So there are the matter particles, the fermions, right? Like the quarks or the electrons. And then you have the gauge degrees of freedom, the gauge fields, like the electromagnetic field or the gluon field, right? So we have different kinds of particles, right? And so we have to have different kinds of species. And on top of that, these particles can exist in many species of this particle exist. For example, they can have different charges, spin, color, flavor, and so on and so forth, right? While, for example, your beryllium atoms of your ion trap are all beryllium atoms, are all the same, right? So you have to be able somehow to encode this thing in your simulator. And finally, most importantly, actually, the most important problem is that this matter degrees of freedom and gauge degrees of freedom interact in a very complicated way that is dictated by what particle physicists call gauge symmetry, right? So there is some local symmetry constraint that the combined motion of matter and gauge fields have to obey, right? And of course, your poor atoms or photons or particles or whatever, they know nothing about this symmetry, right? They have their own Hamiltonian, and you have to find a way somehow to encode these complicated interactions in your native hardware, right? Okay, so this is, as I said, this is a very difficult problem. This is very challenging both for analog and digital quantum simulation. So what do we do? So there was some recent progress in one example, which is the example of electrodynamics, right? So electrodynamics is one of the fundamental quantum field theories. Well, it's not fundamental, but it's one of the quantum field theories you may like to realize, right? So this is describes the theory of electrons and positrons interacting with photons, right? So in particular, the progress was achieved for a simplified version of quantum electrodynamics, which is quantum electrodynamics in one dimension, right? In 1+1 space-time dimension. So what goes under the name of Schwinger model, right? So this is, of course, okay, on the one hand, of course, this is done because it's easier, right? So you have to start somewhere. But actually, I think most interestingly is the fact that this simplified version of quantum electrodynamics actually shares some non-trivial features that are with the higher dimensional gauge theories of interest, for example, quantum chromodynamics. For example, the phenomenon of quark confinement. I'm sure you heard it in the previous talk by Dr. Brewer, right? So this phenomenon of quark confinement plays a crucial role in the theories of strong interaction, and it is present in this lower dimensional version of quantum electrodynamics. So there are reasons why you would like to perform quantum simulations of this simplified theory, right? So, okay, so the monster that you would like to simulate is the following. So this is the Hamiltonian of quantum electrodynamics in a one-dimensional, in 1 plus 1 dimensional space-times, right? So this has 3 pieces. One piece describes the mass of the electrons and positrons, the mass of the fermions. One piece describes the gauge invariant interaction, so the minimal coupling between the fermions and the electric field, right? In 1 dimension, we have only electric field. We don't have magnetic field. And the last piece is the energy associated with the electric field, plus possibly a background electric field. Okay, so this is the Schwinger model, the lattice version of the Schwinger model of quantum electrodynamics. So we want to put this complicated matter and gauge dynamics in the we want to encode it in our quantum simulator, right? So basically, okay, before that, let me try to visualize what kind of processes happen in this theory. So imagine we start from the vacuum, right? So there are basically in the links of this one-dimensional chain, we represent the fermions, right? And on the sides of this chain, we represent the fermions, and on the links of this chain, we represent the electric field. The electric field is like a tower, can take many values, right? So this is like the vacuum configuration where there are no particles and the electric field is zero everywhere, right? Now, some of the processes described by the dynamics of this Hamiltonian look like the following. So when we act with these interactions on this link, basically we create a particle-antiparticle pair, so an electron-positron pair, right? And the value of the electric field between these particle-antiparticles is correspondingly adjusted in such a way to respect gauge invariance. So this obeys essentially the Gauss law, right? When you cross a particle, the electric field changes. There is some electric field created by the particles. Now we can repeat this process in other locations. For example, here on the left, we create another particle-antiparticle pair. We can recreate, and then we can annihilate this particle-antiparticle pair here and create a longer string of electric field, right? And we can go on and create another particle-antiparticle pair, annihilate, and create an even longer string. And then we can even create another particle-antiparticle pair on top of that and raise the electric field even higher, and so on and so forth. So basically, you should imagine the quantum many-body dynamics generated by this Hamiltonian as a complicated superposition of all sorts of processes of this form, right? This is in a way that is described by the parameters of this Hamiltonian. So this is what we want to encode in our Rydberg atoms or trapped ions or optical lattice or whatever your imagination can achieve, right? So basically what we were able to figure out is how to encode a simplified version of this quantum electrodynamics using Rydberg atoms. So I say simplified version in the sense that we allow our electric field to take only 2 values instead of infinitely many values. So this is kind of a, if you wish, a low energy approximation of this theory. But in the limit where you allow for more and more values of this electric field, you recover the full quantum electrodynamics, right? So in this simplified case, essentially we realized that you can map the configurations of particles and fields in this quantum link model, which is the name of this truncated version of quantum electrodynamics. You can encode it in the configurations of Rydberg atom arrays in the blockade regime. So in this regime where two Rydberg atoms cannot be simultaneously excited, right? This is why I mentioned this before. And the point I want to stress here is that the gauge symmetry constraint, so the constraint of that matter particles and gauge fields should move together is exactly mapped onto the constraint that two Rydberg atoms cannot be simultaneously excited. So this is somehow a non-obvious mapping, so it's not very, it's not somehow not so analogic, if you wish, as the condensed matter mappings to optical lattices, right? But it doesn't matter. It's a mapping, it works, and you can map all the quantities from one side to the other and study dynamics, quantum electrodynamics, looking at the evolution of your Rydberg atoms, right? So here you have to believe me, there is a dictionary between the states in such a way that every possible local configuration of matter and the electric field maps to a given configuration of the Rydberg atoms. Okay, once you map the states, you can ask what is the corresponding Hamiltonian. And here we have essentially a stroke of luck in the sense that the native Hamiltonian of Rydberg atoms is already what you want, is already, upon suitably identifying the parameters, is already the Hamiltonian of the quantum link model. So here, somehow we were a bit lucky, right? So we have a mapping between the states, a mapping between the forces, the Hamiltonian, and finally we want to be able to access the observables, right? The corresponding observables. And here you can do that. So this figure shows numerical simulations, right? So on the left you see the dynamics of the Rydberg atom chain. You see that two bright spots can never be beside each other because of the Rydberg blockade, right? So this is the evolution. So horizontally you have space, vertically you have time. This is the space-time evolution of your Rydberg atom chains, prepared in a state that corresponds, within the mapping, corresponds to a uniform string of electric field. So in the vacuum of particles in presence of an electric field. And this is the corresponding dynamics, mapped one-to-one to the dynamics of Rydberg atoms. And also here, this simulation shows the full Schwinger model, so the untruncated Schwinger model, which signifies that this truncated version is more or less doing what the full quantum electrodynamics problem would do. Right? So you have, in this case at least, you have sort of a full dictionary, right, between the Hamiltonian, your target Hamiltonian, and your quantum hardware. In this case, your Rydberg atom arrays. Okay, so I just want to close. Can I take another minute? Yes. So my final slide is basically okay. Now that you have a way to encode your quantum field theory, if you wish, on your Rydberg atom chain, right? So the question is, what kind of physics can we simulate, right? So as you heard in the previous talk by Dr. Brewer, essentially one very interesting thing to do with quantum field theories is to study collisions between particles, right? So basically, okay, so this is, I won't repeat the story. So here, essentially, this is a very important problem in particle physics. And essentially, because it's a very difficult problem, it's kind of an outstanding goal for quantum simulation, like an outstanding long-term goal for quantum simulation. So this is what you can essentially wonder if some cartoon version of this problem. Of course, this is what we can do in the setting that I previously illustrated, is very far from what our colleagues in particle physics would like to do presently, right? So this is kind of there is a huge gap to cover for there before we can actually simulate something that solves some actual problem in particle physics. But it's a legitimate question whether at least the principal ingredients, right, can be realized with present day machines, right? So what we were curious essentially is to study meson collisions. So mesons are like bound states, confined bound states of electrons and positrons. So I told you that in this one-dimensional version of quantum electrodynamics, electrons and positrons are confined, pretty much like quarks in theories of strong interactions, right? So you can imagine to prepare two wave packets of these mesons, right? So two bound states prepared with a given momenta, right? And so this is the initial state you want to prepare, and then you want to run the real-time evolution, right? So you want to encode this in your Rydberg atoms, run the real-time evolution, and measure, for example, things that you would be interested in particle physics, for example, the scattering matrix of this collision process, or you can even do more, as I'm going to argue. Right? So this is kind of the protocol that you want to realize, right? And in this paper, with collaboration with Federica Surace, we have shown essentially how to perform these mappings and these building block steps, right? So how to prepare, in particular, the initial state, so which is this sharp mesonic wave packets with an arbitrarily well-defined momentum, right? And then to run the evolution and to measure the relevant observables. So remember the list of requirements that are needed for a quantum simulation, right? There is the initial state, there is the Hamiltonian, and there is the observables, right? So a possible observable of interest is the scattering matrix, right? And we have shown how to use the capabilities of the quantum simulator to access this quantity, right? Now, I want to just close with a remark that, of course, this is, as I said, there is a huge gap to bridge to do something that is of interest for current particle physics, for example, simulate a relativistic heavy ion collision, right? But on the other hand, the reason why we think this is interesting is that there are things that you can do using a quantum simulators which you just cannot do in nature, right? So one of the things that quantum simulator naturally gives you access to, for example, is that it allows you to watch inside the collision, right? So this is something that is completely unthinkable in nature, so in actual particle physics experiment, right? Here we have full control. No? We can even stop the evolution and look what's happening and understand the processes that are involved, the complicated processes that are involved in a complicated collision, for example. And second, we can play with the parameters. So in nature, the value of the forces, the coupling constants, are just given, right? We can play with it. So here, instead, we can change, right? This is a simulator, right? So we can do whatever we want, or maybe not exactly whatever we want, but we have a large degree of tunability, right? So we can play with the parameters and explore the predictions of the theory beyond what would be accessible in actual nature, and this perhaps would allow us to discover some other effects or some other physics, right? So there are reasons to believe that this kind of approach someday will be extremely valuable for studying, even in this that is probably the most difficult goal for quantum simulators. Okay, I think I'm done, so let me skip this drop distance and just jump to the final slide.